Okay, this is a slightly modified version of our circuit that's under test. I'll run through it quickly. We have our 9-volt battery supply, and we are going through one 22 ohm resistor into a cap. We then have a diode, which is a 1N4004, then another cap, another 22 ohm resistor, and another cap. From that cap there, which will be feeding our device, we go through to the device, and I have a small storage cap here for the device, so as we can smooth out any pulses between that cap and our device here, or our little circuit. And then of course, as in the schematic, we are going through a 1N4004 through an LED, which I've changed to a small white one, back into our second cap. That diode stops any of the current going back into this cap, and that resistor, it can only be dumped into that cap, which then flows through the resistor into this cap. We have our digital multimeter, which we will use first to measure all the voltages, including across each resistor. We are then going to take our analog meter and read the voltage across each resistor. We're then going to use our scope and read the voltage across each resistor. The caps I'm using are 4700 microfarads each, 16 volts. This one is 3700 microfarads, 16 volts. We have our microwave oven transformer secondary as our drive coil, and of course our small coil, which is hooked to base and emitter via a 22 ohm resistor. Okay, so our battery voltage, as we can see, is 9.65 volts. So we'll now go ahead and we will measure this cap voltage, which is cap 1. We have 9.65 volts. We're going to measure the voltage on cap 2, which has a bug crawling on it. And as you can see, we have 9.13 volts. So we've lost 0.5 of a volt, which is typical for your run-of-the-muck diode. So we're now going to go to cap 3. Once again, we have 9.13 volts. So that cap there is what is supplying power to our circuit here, and that is the voltage to which it is applying the circuit with. Okay, so what we're going to do now is we're going to measure the voltage across each resistor. I'll turn that back on. Okay, so this is the resistor from our battery, straight through that resistor into the first cap. And we have 2.3 millivolts across that first resistor, which is 22 ohms. And that of course will be DC. So now we're going to measure the voltage across our second resistor, which of course is also 22 ohms down to the T. And you can see we have 5 millivolts across that resistor. Now the one thing we didn't measure, and I'll put the lead back on the common rail, which is the wrong way around. Awfully hard to do one-handed. Okay, we're back on the common or negative ground, whatever you want to call it. And of course we're going to measure the voltage in this cap here, which we'll call cap 4, which is of course part of this system. 9.18 volts. We go back over to this cap here. 9.20 volts. 2.1. And the reason we are having hiccups here is because the circuit has stopped. Right, we're up and running again. So we'll have to give that a little time to settle in. Every time you go and touch one of these connections with the multimeter, sometimes the circuit will stop. So she's a little bit delicate. Okay, so we're still hooked on our ground and our last cap, which is showing us 9.13, and we will now hook it back onto this cap, and our light didn't go out this time. That is showing us 9.12, 9.13. So pretty consistent right through when we take into account our diode drop in voltage. So what we'll do now, get rid of that meter there out of the equation, and we will hook our analog meter. We are set on 250 millivolts, which is as low as this one will go. And we are going to have a look at the voltage across each resistor. Okay, it's going to be a bit hard to see, but every division there is 5 volts, so you can see we've got 5 millivolts. So you can see we have about 2 millivolts there, according to our analog meter. So once again, swap it over to our second 22 ohm resistor, and now you can see we are on the first mark, which would be our 5 millivolts. So the analog and the digital meter are reading pretty much well spot on with each other. There won't be any mistakes because it is DC we're dealing with. There is no traces of any pulses going across there, because the current we are drawing is so little and the frequency is very high, you'd hardly notice a ripple. Okay, so we will zero our scope out. We are set on the 5 millivolt divisions. As you can see there, we have about our 2 millivolts. Try that again. Okay. So yes, we have our 2 millivolts. So we know what we have across this resistor. We've measured it with a digital multimeter, an analog multimeter, and the scope. We'll now place it on our second 22 ohm resistor. Once again, we have changed our reference point, so we keep an eye on the scope, make sure it is zeroed out, which it now is and you can see we have our 5 volts, or 5 millivolts across that resistor. So there isn't any way I can show it any more clearly at the moment, until such time as we get our new scope and all that jazz, but that's you can't get any more accurate than that. And as you can see, we are set on the 20 microsecond per division on our time divisions, and there isn't a bump or a ripple in it, so the meters would be reading correctly along with the scope, so there can be no argument there at the voltage across each resistor. So you can now use Ohm's law to calculate the current going into the system, which is our DC current, or the power going into our system, DC power, and you can also calculate the DC power across that resistor there, which is in series with the first one, only we have a diode. So we would actually have a voltage drop across that resistor thanks to the diode, but still we have a higher voltage across that resistor than what we do the input resistor. Okay, so I'll post this video. I'll draw up a quick schematic for it as well, so you can check it out. Anyone that wants to build it, try it themselves, welcome to give it a go.